Okay, now this is the question in front of you that we discussed about the momentum conservation and center of mass motion along the same line. Now, this is a shell at origin explodes into three fragments of masses 1 kg, 2 kg and m kg. That means m here is unknown. Okay, the fragment of mass 1 kg and 2 kg fly off with 12 meter per second, 8 meter per second along y axis. That means for 1 kg this is going along 12 meter per second along x axis. We can write I cap. 2 kg mass is going with 8 meter per second along y axis, so j cap. If m kg flies off with 40 meter per second, that means this m has velocity of 40 meter per second, but we don't know the direction of that, so we cannot denote ij in that. Okay, that is magnitude of velocity given to you. Okay, the total mass of the shell is what? That means what is the total mass? Total mass will be m total will be 1 kg plus 2 kg plus m, which you have to find. Okay, now how will we apply the conservation of momentum part here? See, there was a shell, that means at rest. Okay, it broken into three fragments. Again, explosion part is there. Since explosion is because of internal forces, so external force is 0 in this. When external force is 0, you can say that P initial equals P final. Okay, P initial was 0, so P final has to be 0. So P final you will write P of 1 kg plus P of 2 kg plus P of m kg. P of 1 kg will be 1 into 12, that is 12 I cap, plus 2 into 8, 16 j cap, plus P of m kg. Okay, now P of m kg you can write as minus 12 I minus 16 j. You know that velocity is 40 meter per second for that m mass, that is magnitude. Okay, so in magnitude wise when you write, this will convert to magnitude of momentum of mass m and then this. So in magnitude wise, P of m will be root of 12 square plus 16 square, which is root of 400, and that is 20 kg meter per second. Now when Pm, momentum of this mass m is 20 kg meter per second, so we can assign that, okay, we can assign that this part here we can write mass into 40, which is given for this mass m unknown, equals to 20 kg meter per second. That means mass will be 0.5 kg. Okay, so m is 0.5 kg, so total mass is 1 plus 2 plus 0.5, that is 3.5 kg. Now, one more thing is explosion energy. Let's see a question. A mass of 3 kg, okay, explodes into 3 fragments of same mass. Explodes into 3 fragments of same mass. Now, given that one mass has momentum 4 I cap, another mass has 2 J cap. Okay. Now you have to find the total energy of explosion. Okay. Now see, this is the question given to you, and given that one mass has momentum 4I, another mass has momentum 2J. That means now here the talk is about momentum. Momentum talk is there. So if I assign these two masses, one will have 4I cap and one has 2J cap. Okay, momentum are given. That means if I say this is P1, this is P2. P3 we don't know, and similarly we have to find total energy of explosion. Total energy of explosion, how to define that? If I say 3 parts were there, how they are coming into picture? Only because of explosion, and that explosion takes place because of internal energy of that. That means due to consumption of internal energy, there is explosion, and that explosion having different momentum. That initially it was at rest, but now they have momentum, and momentum whenever there is a speed. That means there will be energy in form of kinetic energy, or you know that you write kinetic energy as P square upon 2m. Okay, so again we will use the same concept of conservation of momentum. P initial is 0, P final is 4I plus 2J plus P3. That means for the third particle we don't know what is momentum. So P3 will be minus 4I minus 2J. That means P3 modulus magnitude will be root of 16 plus 4, that is root of 20 kg meter per second. Okay, and Pi modulus is 4 kg meter per second, and P2 modulus is 2 kg meter per second. Now P3 is root 20 kg meter per second. So total kinetic energy will be total energy of explosion, which you write P1 is square upon 2m, P2 is square upon 2m, P3 is square upon 2m. Okay, so P1 is square is 16. So 16 upon 2m plus 4 upon 2m plus root 20 whole square, that is 20 upon 2m. These three are equal fragment, that means all having mass of 1 kg. Okay, now that means this will be 8 plus 2 plus 10 joules, which is 20 joules. So this is the total energy of explosion. Now, in this, we will deal with one or two problems of conservation of momentum plus energy. Okay, right? Now this. Let's start with some example how to use both. Okay, let's see. A plank is there. Okay, kept on horizontal surface having frictionless floor. Mu is 0, so there is no friction. One mass m is there and this wedge having mass m. Okay, this is the t equal to 0. At t equal to 0, this is the position. That means a mass m is kept and all the surfaces are smooth. This surface is also smooth. Mu is 0. And this is wedge. Now, and this mass m is released. At t equal to 0, that mass m is released. So what will happen? You have to find that velocity of wedge and velocity of mass m. Okay, after the smaller mass m reaches bottom. Okay, bottom, or if I assign point A and B, so at B, right? Now you have to find velocities. When this will go down, see, there is acceleration downward g, so there is a force downwards. In x direction there is no force. Okay, in x direction there is no force. So initially there was no acceleration along x direction, finally also there will be no acceleration, but there will be normal. At a certain point there will be normal. Okay, when this mass, suppose m is here, there will be a normal, right? These two normal components, and because of this normal, see clearly, this normal, there will be forces, component of normal. This component of normal will push this mass m, that wedge, backwards. Okay, while this is going downwards. So because of this component of normal, this wedge will go backwards. So finally what will the situation arises here is that mass, that wedge of mass m will be going backward with some velocity, say vm, and while leaving the surface, that m will have velocity of vm. From where that velocity is coming? Because initially there was no momentum along x direction, right? Or there was no any force along x direction, but because of internal force, that is because of normal, they are having movement, and that small mass m is going down by some height h. Okay, that means loss of potential energy is there. Okay, that is what, there is a gain in kinetic energy of the system, right? So for that, what we will do, we will first find the relation between these two velocities. Okay, and that we can find by P initial equal to P final along x direction. That means we can write P initial along x was 0. So P final along x is also 0. Okay, that means from this we can write 0 equals mass of wedge, velocity of wedge with minus sign, because of this I am taking as minus, this is as plus, plus m into v of m. That means m vm equals m of vm. Okay, this is one relation that you have found. Now that velocities are coming into picture only because there is a loss of potential energy of this small mass m. That means you can also write this in the form of energy conservation. There is no external force, so EF will be equal to EI, right? EF will be equal to EI. E final will be the half m Vm square plus half m Vm square. Initial energy is only because of potential that is mgh. Okay, now from here we can get relation of Vm and V. If I take, suppose, if I want to find velocity of mass small m, okay, then we can substitute the value of small m as capital M, sorry, this V of capital M as m of V small m upon this capital M, so that we can substitute in place of the capital M velocity here. So this will be half m Vm square plus half m square Vm square upon m square equals mgh. One m will be cancelled out. Because of this m, also one m will cancel out. Okay, so remaining will be half Vm square as common, so 1 plus small m by capital M equals gh. Okay, now you can write here. You can write here. So Vm we can write as 2gh upon 1 plus m upon capital M whole root. This is the velocity of smaller block m. Similarly, when you will solve for the capital mass, then we have to substitute the small mass velocity, okay, and then you will write in place of the small mass velocity as mvm upon m. That means you can write small mass velocity as m velocity of capital mass upon small mass m, and then substitute back to the equation of energy and you can get the velocity of m. This you can do. Pause the video and you can find this velocity. One more with spring block system. Let's take spring block system. Suppose this is 2 kg mass going with 10 meter per second. This is 5 kg mass and going with 3 meter per second. Okay, this having spring constant as 1120 Newton per meter. Okay, now this is going with 10 meter per second, this is going 3 meter per second, so there is velocity of approach. That means they will go and collide. Okay, now you have to find the maximum compression in spring. What is the maximum compression in the spring? So this is the initial situation. Okay, and spring again as a system has internal forces, because spring, take two system is going, so as system, whatever spring force is there, they become internal forces, right? If this is going in this manner, okay, some force is there, so spring will have opposite force, which is minus kx. Okay, the same way, when this is going forward, so spring will have force in this direction. Okay, now as a system, spring force will have opposite and equal effect or magnitude of forces. The same thing will happen here when they start to move together. Like there is 5 kg block and here 2 kg block. It will go and compress the spring until that point they start moving with same velocity. Okay, while compressing they start moving with same velocity. Okay, now at the maximum compression, okay, they start moving with same velocity. V is same at maximum compression. Okay, and again the spring force as a system will have all the internal forces equal and opposite. Okay, right? Now, so how will you do it? First, you will conserve momentum because net external force is 0. So, we'll conserve momentum, and then again we will use the conservation of mechanical energy because there is no external force. So, EF will be equal to EI. That is, let's do it first. Now, situation is initial momentum you write as 2 into 10 plus 3 into 5, which is 35 kg meter per second. Okay, now final momentum at the maximum compression, because we have to find the maximum compression they will be having with going with same velocities. Okay, now 2 kg also have same V and 5 kg also has same V. That means 2V plus 5V, which is 7V kg meter per second. Now, a spring is internal force. Spring provides internal force and spring force is internal force. So, for a system, right? So, you write Pi equals to Pf. From here you will get 35 equals 7V. That means V is 5 meter per second. That means at the time of maximum compression, this V is 5 meter per second. Okay, that V is 5 meter per second. Okay. So, now we have to conserve energy. How will we write? See, form of energy is work done by non-conservative force, work done by external force, work done by pseudo force is equals to EF minus EI. Final mechanical energy minus initial mechanical energy. There is no non-conservative force, no friction, no external force, no pseudo force. So we can simply write EF equals to EI. Finally, the energy written in the form of spring potential energy plus the kinetic energy of block. So you write for block system half. They have same velocity, so you can write simply as mv square as half 5 plus 2 5 square plus half k. K is 1120 into x maximum square, right? The time of maximum compression is the initial kinetic energy. Initial is half 2 into 10 square plus half 5 into 3 square. So when you solve this, this will be 7, okay, and 25. So 175 upon 2, 25 and 7 plus 2, 560 x square equals 100 plus 45 by 2. Okay, on solving this you will get 100, 45. So x square equals, okay, let's do it, 100 minus 175 by 2. When you solve this equation, you will get, I think, 1 by 4 meters. Okay, solving this equation, you will get 1 by 4 meters. So solve it and check. This is 1 by 4 meters. Okay, so at the time of maximum compression, they have same velocity, and the maximum compression you get is 1 by 4 meter, that is 0.25 meters. So this is your answer, and this is the way to use conservation of momentum and conservation of energy together with the center of mass problems. Let's take one more spring block problem, and we can say, suppose two blocks are there connected with spring. Okay, one block having mass 10 kg and one mass having mass of 4 kg. Okay, this is the situation at t equal to 0. Okay, now an impulse is given to 10 kg mass, providing speed of 14 meter per second. Okay, you have to find velocity of center of mass will be what? Now, impulse is a very short term force. For that, delta t tends to 0. For that, force is given to provide 14 meter per second to 10 kg mass. That means at just t plus dt time, this 10 kg block will achieve 14 meter per second. Okay, but because of this spring, this 4 kg will be at rest. This 4 kg will be at rest. Just after this block only get the speed of 14 meter per second, that block will be at rest because of the nature of a spring. It will take some time. Okay, that means this will go and compress beyond mean position, then they will start moving together. So for that, now you have to find VCOM. So it will be 10 into 14 plus 4 into 0 upon 10 plus 4. That means again 10 meter per second. Okay, so this is the center of mass velocity just after, okay, remind that just after 10 kg gets impulse. Okay, so this is the velocity.